This information is brought to you by Charles Sturt University.
Hi, this is a video just doing some revision questions. So what we have here is we've got a surface, z equals x squared minus y squared, and just want to get a sense of what it looks like and sort of other questions we can do with it. So part A asks us first, let's work at the level curves for this particular surface and given various contour points, so plus minus 1, plus minus 2, and 0. So to work out A, so the contours pretty much are the form x squared minus y squared is equal to some fixed number, where k is going to be each of these different values we have at the top here. So we're going to try to draw them all, essentially. Let's do them in order. Let's do the middle one first. Let's do x squared minus y squared equals 0. That's going to be the level curve when z equals 0. Now it's a difference of two squares. On the left hand side here. And so when you've got a product of two things is equal to 0, that implies either the first one is 0 or the second one is 0. So just drawing a line. So x minus y equals 0 is just the line y equals x. Just look at that. And x plus y equals 0 implies y equals minus x, which looks something like that. So this is the z equals 0 case. That's one option. So the other curves look like x squared minus y squared equals, say, positive 1, for example. So in this case here, it's not 0 anymore, so you can't factorise that. But you go, hold on a sec, when you got a difference of squares equals a constant, that's going to be a hyperbola. The asymptotes of this sort of curve is given by replacing the 1 by 0, which we've done. So the blue lines are the asymptotes. And so really we're just going to work out two things. One thing really is just the vertex. Once you know the vertex, everything else is fine. So when you've got a difference of two squares, you let whatever you're subtracting on. So if it's a positive number over this side, whatever's negative you just let be 0. And so x squared equals 1. Therefore x is equal plus or minus 1. And so just drawing those on, so at minus 1 and at 1 are our vertices. And so since it's a hyperbola passing through these vertices, sorry, I got the z equal, so I'm at the y be 0, that forces the x to be plus or minus 1. Get these vertices. So now we know the vertices, know that blue line's the asymptote, we can just connect them up. So that's what it looks like for equals 1 case. In a similar way, if we had x squared minus y squared equals minus 1, well, it's also going to be a hyperbola, but we can multiply both sides by minus 1 to give you y squared minus x squared equals 1. So you can see it's almost the same curve, except the roles of x's and y's are reversed. So therefore the vertice would now be on the y-axis instead. Have that sort of shape. So I just reflected about the y and y equals x. So this is z equals minus 1. So another one we want to do is x squared minus y squared equals 2, and remember 2 is equal to the square root of 2 all squares, one way of thinking about it. So a common way to standardise is to make this the number on the right hand side into a 1. So divide both sides by 2, or root 2 squared, so you get x on root 2 squared minus y on root 2 squared equals 1. And when you net sort, that's a standardised, definitely hyperbola. Difference of two squares suggests hyperbola. So in either form, you could have worked out the vertex by going, whatever the minus is, just let that to be 0. When y, so y is 0, x squared equals 2, x therefore must be equal to plus minus root 2. Or if you got it in the standardised form, the vertex is plus or minus whatever's on the bottom of the x value, and then 1, y is 0. So either way, you can see that the next curve is at root 2, which is on plus minus 1 root 2. Which looks something like that. And again, by symmetry, you can draw the z equals minus 2 case in exactly the same sort of fashion. So a few things you can see from this picture is that as you're going further away from z equals 0, so the xy plane, the line's getting closer to each other, so it's getting steeper. And it's sort of curving away in each direction. So now from our level, our contour plot, as we've got here, we can now work what the surface looks like. Okay, so let's just try to draw the axes, which I'll just clobber. So this is the xy axis, which match up to what I've got in the picture here. So on the x-axis, this one here, we can see that as you're going, so it passes the origin, so it actually does hit the origin here. As you're going away, you can see you're getting higher red values. So it's going to actually so it's going to look like a parabola in that sort of direction. Looking on the y-axis now, you can see that as you're going away, you're getting negative values. The green's all negative. So it's sort of going to curve down this direction. Dotted line over here. And indeed, as you go, and so see if you take any line across my level curve here, you'll also get a nice sort of parabola going around. Try to draw the other side without clobbering the image too much. So what we're sort of getting is curving one way and lots of ribs coming off it. Let's just do one. So what we're getting here is what's called a saddle. So it curves one way, the other way, the other way. And so you like the top of a horse, essentially. That's the basic idea. So I've got our picture, our saddle point, and again, my original picture showed the x, y, z axes too. So I gave it a context of which the direction it is. So this picture here is good for identifying clearly, where it sits in the place, and it shows you that the vertex, or the center really, is at the origin. So the critical point of the surface is at the origin. Where the second picture doesn't get the black line in the way, but you've got no idea where it fits in space. So just showing you how to practice it. And again, you could have done traces in other directions to help classify that surface if you wanted to. You don't have to just use level curves. But level curves is one way that we've seen previously of working a surface. Now we do other things with surfaces like we've done before. So something else we've done is things like find the tangent plane. So we've got our curve. Let's do the tangent plane. and say x equals 1, y equals 2, and if you plug those two values in, you get z equals minus 3. So the tangent plane in general is z minus z naught times by the partial derivative of the function. So we're writing in z, we'll run as zx. At 1, 2, x minus x naught, and then plus the partial derivative with respect to y at our point. I should be writing x naught, y naught here. That's the sort of a general sort of format we have here. So it's z minus the minus 3 is equal to some partial derivatives, which we need to find out. So we should do that, right? So the x partial derivative is 2x. The z partial derivative with respect to y is minus 2y. So the z partial derivative at our point in question, 1, 2, is I just plug in x equals 1, y equals 2, you're getting 2 times 1 gives you 2. And the z partial derivative at 1, 2, again plug in x equals 1, or more particularly y equals 2, we can get it minus 4. So again, z plus 3 is equal to this number, which worked out to be 2, x minus the x value of our point in question, plus our partial derivative, minus 4 times by y, minus 2. And now it's just a matter of cleaning it up, really. So z plus 3 is 2x, minus 4y, minus 2, plus 8 gives you plus 6, and then subtract 3 on both sides, gives you plus 3. And you can rewrite in lots of forms, so 2x minus 4y minus z equals minus 3 is a sort of standardized format. Lots of choices. Let's put a tick up here though, to show that at some point in time, there's lots of acceptable answers. So this is simplified down. That's useful. And so the purpose of a tangent plane is so long as you're close to the point in question, so long as you're close to this point, the tangent plane actually is a good reflection of the surfaces, and you can do things like approximations, that sort of idea. So it's quite useful. We can do other stuff too. Maybe we can imagine that this saddle point we've got here is on a mountain range. If you're walking around, you get saddle points occurring in nature. So the one I drive through all the time is coming down the Blue Mountains. You got a saddle point. So the road just managed to just rest on the saddle as it's going down at Victoria Pass. So you might have a question, well, going on this saddle point, what's the different parts of it? Let's find the slope in a particular direction. Let's find the slope of this particular surface in the direction of I plus j. So in order to do that sort of question, we pretty much want to know the directional derivative in a certain direction at a point. And we only need to know the x, y points, really. But in order to work directional derivatives, you really need to know the direction, not the magnitude. So I will often hat on it. So in this case, the direction we want is I plus j, which if you think normal axis, that's sort of northeast. But we want to be able to, in order to use it, we really need to standardize I divide through by its length. So the length of u, or squared at least, is going to be the sum of the squares of each individual component. So it'd be 1 squared plus 1 squared, which is 2. And so taking the square roots, the length of u is going to be root 2. So to standardise it, to normalise I should say, to make it into a unit of length 1, we have to divide by its length. So 1 over root 2i plus 1 and root 2 j. Now you could write these normal coordinates, just 1 and root 2, comma 1 and root 2. The reason why I've done I and j is to distinguish it from the other coordinates. Only 1 and 2 we've got earlier. So I want to specify one is the direction, one is the coordinates on our particular surface, etc. So when you've got directional derivative, to work them out, you just take the dot product of our direction and the gradient vector. So in this case, the gradient vector is just the vector of all the derivatives, which we worked out a second ago, is 2x and minus 2y. And as a matter of fact, we can work out what it is in this particular case, which is what we know here, right? So you can plug in x equals 1, y equals 2, which we did before as well. So you get 2 minus 4 is the gradient vector at this particular point. So taking the dot product, we've got the dot product of writing sort of just vector form now. 1 and root 2, 1 and root 2, the two components. Dot products with the 2 minus 4. So I can see I used the ij just as a convenience earlier to distinguish between the two, but at some point in time you need the calculations. And when you do dot products, you just multiply corresponding entries. So you get 2 and root 2, and then you sum them all up. So plus minus 4 and root 2. If you do the calculations, you're getting minus root 2 in the end. So the slope in negative means it's going down. So we're heading downhill at that point in that direction, and this magnitude is minus 2. So questions that sort of related to this sort of question is, well, now we know the slope in one direction. Well, what about, can we work out the direction where it's the steepest going up, which is the steepest direction? And if you know the steepest direction, well, what is the slope in that direction? Well, we know it should be positive, it's steepest descent. What is it? Well, the answer is quite straightforward. So steepest descent, the direction of that is, direction of steepest descent is just in the direction of the gradient vector. So I, in the direction of 2 minus 4. And the magnitude, sorry, the actual value of the slope itself, is the length of the gradient vector, which in this case would be the square root of first component squared plus the second component squared. So 2 squared is 4, 4 squared is 16, sorry, square root of 20 would be the direction in that case, and which is steep, right? So root 20 is 4 point something, slope of 1 is going to be hard for a car already. When you got up to 4 and a bit, not quite 4 and a half, it's you're not going to get a car up there, and I mean you can't walk up there either. You're probably having your hands and knees a bit to get up there in that direction. So that's the idea. So just a directional steep descent is just the gradient vector, and the magnitude is its length. If you want a steepest descent, you get the opposite direction, of course. So you just be minus the gradient vector, heading backwards. So that's just a few questions that we have been able to cover previously about surfaces and level curves and just what sort of things you can do with them. And mostly this is sort of revision of what we did in part 1 of the subject. So I hope that helps with your revision and getting ready for the exam coming up soon.